let's do a quick recap of bagging, random forest, boosting, and XGBoost. Boosted trees. XGBoost. XGBoost is something that we'll do this class, today's class. So, but you should know up to here then, right? Okay, so bagging versus random forest. Firstly, what is bagging? As we discussed initially, right, there are various ensemble algorithms. Ensemble algorithms basically mean that they combine weaker models, weaker learning models, and they tend to become a stronger model. So that the idea is unity in strength, right? Strength in unit, basically. So the more, if you remember the stick story, right? Like one stick can be easily broken. 3-4 sticks can be probably a little difficult, but it's impossible to break like 10 sticks together. You guys remember that, right? It's the idea of together we are stronger, right? So what that's the exact concept behind ensemble models. And depending upon how you combine these weaker models together, you have various techniques, right? If you combine them in a parallel kind of a fashion, you have what is called bagging, and what also includes random forest. If you combine them in sequence, you are like in serially, right? You kind of have what is called as boosted trees or XGBoost, right? So what does parallel combination actually mean, and how do you roll with it, right? So there is a tree, there is tree 1, right? This is one decision tree, this is another decision tree, then there is another decision tree, yet another decision tree. Okay, so this is model 1, this is model 2, let's say this is model 3, right? In bagging, what happens is you have first tree, second tree, the third tree, right? So these are 3 different trees that are constructed from the same training data set. Okay, so what you do is basically you give the training data set and it shuffles the data set. It can take random rows from the data set and create the training sample for each tree. And it tries to come up with a different training sample for each tree so that the trees themselves are different. Okay, that's what bagging does. And when I say shuffled, right, there are certain things that happen. The training set can be like 0 to 80, let's say, or 0 to 79, let's say the 80 records that we are taking, right? It might have them in 0 to 79 order, it might shuffle them internally, or it can do something else as well. What it also does is it replace by replacement, right? Like let's say, for example, I have 1, 2, 3, 4, 5 in my list. This is my training data set, let's assume, right? I can recreate 1, 1, 2, 3, 3. This is a subset of my training set, right? My actual training set has 1, 2, 3, 4, 5, but I am drawing observations by repetition, right? So by replacement basically means that if you remember the probability concepts, right? You have balls in a bag and you're drawing those balls with replacement, which means you take a ball, note down the number or the color of the ball and put it back inside the bag to pick it again. So there is always a probability of picking the same number again. And that's exactly what you do with replacement. You guys don't have to bother about it. It's just a concept. If somebody asks you exactly how these samples are being built, you tell them that these training samples are built with replacement. Right, that's it. It's probably going to be an interview question, but it's not going to change how you're going to build the model or anything. It's something that you don't have to bother with. It's something that the model itself trains each tree on. In order to obtain a different decision tree each time, this is what it does, right? It shuffles the data, it picks samples with repetition, it does all these kind of operations in order to come up with a different training set each time it trains a decision tree. So, and this is again what we said, this is n estimators, right? That's the parameter with which you control how many trees you train, right? So in bagging or in random forest also, what happens is parallel, what we mean by parallelly training these models is each model is trained without in isolation. So model 1 does not know that model 2 is being trained. Model 2 does not know model 3 is being trained, right? There is no information exchanged between model 1, 2, 3, and so on. Each of them is working on a copy of the training data set, and each of them is being built up, right? So they all work and then they come up with various decision trees. Each of them individually, these decision trees can be prone to so many problems like overfitting, can be weaker in terms of prediction, because if we restrict them, they become weaker, right? We restrict them by specifying max depth or number of leaves or parameters like that, limits like that, which make sure that the trees don't overfit. But when they don't overfit, they become weaker in terms of their predictions, right? So each of them have only a certain limitation, so only a certain depth to which they can train, right? So thereby they become weaker models individually, because they are trying to avoid the other extreme of overfitting, right? So they become weaker models. So what you do with all these weaker models, tree 1, tree 2, tree 3, is that if it's a regression problem, you supply it with a test set, right? So if you guys remember, again, the age-old problem, price of shirt depending upon cost of cotton, cost of labor, and cost of equipment. Based on these three factors, I'm trying to determine what should be the price of my shirt, right? If you remember that, let's assume that I built a model, a bagging regressor, or a bagging regressor, so to say, right, to predict price of my shirt. What happens is it looks at these three values. Each tree comes up with a prediction for the price of shirt, right? First tree says that price of shirt should be $4, right? Second tree says that price of shirt should be $5. Third tree says that price of shirt should be $4. Now, what do I do? What is my final prediction? I average these three numbers, 4 plus 5 plus 4 divided by 3. And what do I get? 8 plus 13, right? So that will be 12, 4.33, maybe. That's the number I'll get, right? 13 divided by 3, so it will come to 4.33, right? So that will be the number, the final price prediction for the shirt, right? With the bagging model, because I am, first tree says 4, second tree says 5, third tree says 4, I average them out, right? Now, same thing in classification. What happens is, let's say I'm trying to predict, instead of this, I'm trying to predict my iris data set. Let's take that example, right? So I have sepal length, I have sepal width, I have petal length and petal width. And based on that, I'm predicting the species, right? First tree says 1, second tree says 2, third tree says 1. What will be the end prediction in this case? Any guesses, guys?
Do you do the average or you take the most common?
Yeah, so that's the point, right? For classification, we don't take an average. We take the most common, which is the most voted one. So we call this as voting, right? We call this as voting. So we say that the first model or the first decision tree has voted 1. Second decision tree has voted 2. Third decision tree has voted 1. So we consider the most votes among all my models and pick that particular, because average doesn't make sense, right, Susan? So if we take average here, right, it will be 4 by 3, which will be 1.33. What is 1.33 in terms of like the species label? My labels are 0, 1, or 2, right? Remember, Susan?
No, yeah, makes sense.
Makes
so
sense, right?
we only average when it's a regression, correct?
Correct.
Okay.
Because in terms of classification, an averaged number doesn't make sense. It's not a label, right? What we have here is actually qualitative, although we have numbers here because the model can only work with numbers, right? This means something like iris celesica, or this is iris custom, something like that, right? Like they have some specific species names, right? So this is, although it looks like a number, it's a string, so to say, with respect to our meaning, right? It's a species label. So we don't have averages here, right? Whereas, and if it goes back to the concept of in regression, you're trying to predict a number, in a range. So it's a continuous variable, right? In classification, you're trying to predict a category, which is a discrete variable. You guys remember that concept?
Yeah.
So it goes back to that. That's the reason why in classification, you don't take an average. Instead, you look at the voting. Okay. All right. Now, clear with bagging?
Yeah.
Any questions from anyone with respect to bagging? No questions? All clear?
All clear from me.
Cool. So let me know if you guys, any of the others have any questions, okay? So with respect to random forest, now what happens with random forest? It's the same as bagging, right? It's based on the same concept. The only difference being when it generates the tree, instead of just showing it different variation of the training data, it also decides to limit the feature set, right? So that way it is making sure that none of these trees can be even close to each other, right? Can be much more similar. They are very different from each other, and that's how it ensures that each model it trains are different from each other. Okay, so it restricts the feature set. So if we have, as we remember, right, we remember that there are 4 features in the iris data set, but whenever my random forest was training a specific tree, it was only using 3 out of the 4 features, right? So that's the additional aspect that random forest does. Now, I think later they also updated bagging classifier in order to have that max features attribute, which you can use in order to limit or, have features like random forest. And in doing so, bagging and random forest kind of don't have much difference in these days, right? The bagging classifier or the bagging regressor versus random forest classifier or random forest regressor, they don't have too much difference, right? It's probably just the implementation and how things work in both these models at the back end that they might be slightly different, but otherwise you don't see that conceptually they are pretty similar, right? So the other additional feature of random forest is that apart from also shuffling your training data set and drawing samples from the training data set with replacement, right? It also limits the features. It randomly selects a certain number of features to train so that each tree under the random forest is a different tree.
Yeah, so with random forest, with the features, like it does it on its own. We don't tell it how many features to like, it just randomly does it. So say if there are 5 features, it could decide to restrict it to 3 or 4, whatever.
Yeah,
right?
so if you do not specify the parameter called max features, right? If you specify the parameter, then it starts looking at, so for example, right? If when you guys remember the lab probably, right? There was a parameter called max features, right? This is there even in the notes. If you guys refer, there is a parameter called max features. If you don't mention this max features, it will randomly pick a specific number, randomly create trees by exposing them to a specific number of features. Okay. So if you do specify max features as, let's say, 3, then it will try to train the trees with either 3 out of 4 features or less than 3 out of 4 features, because it says max, right? But doesn't mean that you can't use 2 or 1 feature. Make sense?
Yeah.
Right. So it will be 3 or less than 3. So whatever max features is there, it will be this number or less than this number. That's the number of features. Now, why again it has to do this? And so let's say you don't specify max features. Let's say you don't specify max features. Okay. What happens then? Right. That the random forest model might train some trees on 4 features, 4 out of 4. Right. But remember, you specify n estimators as a big value, you are not going to specify 2 or 3 in an estimators, right? You guys usually do 50, 100, 150, 200, 250 or something like that, correct? So if it has to train so many trees, obviously some of those trees will be 4 out of 4 features, some of them will be 3 out of 4 features, right? Some of them will be 2 out of 4, some of them will be 1 out of 4. Now, what happens with boosted trees? Okay, we've seen the parallel combination. Basically, parallel basically means that we are training all these various models in isolation. In isolation, in the sense the models themselves are not communicating with each other. Whereas when you, this is weird. Okay, whereas when it comes to boosted trees, right, it is sequential. Training is sequential, right? It's not parallel. Like in this case, the training is not parallel, it's sequential, which means I train a decision tree first, right? This is a decision tree, it's 1, right? The second tree that I train, the way I train it is learning from the mistakes of the first tree, right? It looks at the residuals of the first tree. Residuals basically mean the errors that the first tree has made, the misclassifications that the first tree has made, right? And then it works to improve those, but in turn it might make some more mistakes. The third tree then learns from the second tree, right? So here what is happening is you are training one tree at a time. You're not training like all the trees parallelly like how you did in bagging, right? You're only training one tree at a time, and each subsequent tree learns from the previous tree. So here there was no information exchange. These trees are not learning or communicating with each other. Here, the successor, the next tree that you will be training is talking to the previous tree in the sense that it's taking the residuals from the previous tree and trying to improve upon those errors, right? And this is a reason. So why they are also called as, like, one variety of this tree is called as XGBoost, which is gradient boosted trees, right? And the gradient here is the cost function, right? Cost function is nothing but the errors that a specific tree is making. Gradient boosting is basically the idea of minimizing the cost function. Okay, now what is cost function? What exactly is happening over here, right? So let's say, let me take a new page. Okay, so let's say this is my linear regression model. Okay, you guys remember this from last class?
Yeah.
Right. So as we discussed, these are the errors, right? So, and we thought, we kind of discussed a couple of metrics for these errors. Can you guys tell me some of the metrics? This is linear regression, right?
Mean square.
Come again?
Mean square.
Yes, mean squared error, right? That's good. Another from somebody else?
R square.
Somebody else. Okay, R squared. Yes. One more. There are actually two more, but one is good enough in this case.
Did we do an over on that? No,
Sorry?
never mind.
Susan, so think about, guys, think about MSC. We've also talked about something else.
Root mean square.
Yeah, root mean squared error, correct, right? So it's simple. Root over mean squared error is root mean squared error. That's it, right? So MSC, R squared, root mean squared error. So these are various metrics. These are also referred to as cost functions. Nothing great here, okay? So sometimes in interviews, people might ask you a question saying, hey, what is the cost function for a regression model, right? And you'll be like, hey, what is this cost function? Have I even studied about it? Nothing major. It's just these metrics that you use to evaluate these errors. So why it's called cost function is because these errors, right, that you see here, these pink lines that I've drawn, for this data set, when you measure them, so when you measure them with by squaring these distances, adding them up and taking an average, that is what is called as MSE, right? Now that's a specific formula for you, right? The formula of here for this would be sigma because I'm adding them, right? Error, let's say I, where I ranges from 0 to all the way up to n. Let's say this is 0.0 and this is n, right? So error of each of my points, right? Square of these errors and then divided by total number of errors n, right? This is the formula for mean squared error, okay? And this is my cost function, okay? Why? Because what is my cost? If I have to calculate my cost, I have to add all the errors here, and this is basically a function, and the formula can be called as a function, and that's the reason why they call it the cost function. But there is nothing major about it. This formula is called the cost function. When you calculate it, what you get is called the MSE, or mean squared error, right? You're calculating the error. Now, the cost function can also be RMSE, in which case the function will be the same thing with just a root over things. That's it. Root mean squared error. That's it, right? R squared has another formula. You can again use those. It's a ratio basically. So you use the ratio, and then that ratio formula becomes the cost function, right? There's nothing major. Cool. If anybody asks you about cost function, what are you going to say?
It's the matrix used in calculating the errors.
It's the formula that you use to calculate the metric. That's it. Right? That's your cost function. So if somebody asks you what are the various cost functions for a regression model, you start talking about MSE, RMSE, R squared, MAE, mean absolute error, all these. These are the cost functions. Now, if somebody asks you what's the cost function for classification, what are you going to say?
Accuracy.
Sorry?
Finding the accuracy.
Yes, accuracy. But so there are specific names for that. So just read up about them. Log loss is one common thing for classification. So log loss or all of these things, right? At the end of the day, they are similar to accuracy, right? What you're doing with accuracy is you're just trying to measure the ratio of misclassifications to classifications, right? That's your accuracy. How many did I miss? Or how many did the model miss versus how many did it get correct, right? That ratio is what you call as accuracy. Log loss is basically you take a log of all these, the number of errors that it basically generates, right? The number of misclassifications it has. The reason why you take log loss as a function is because when you have no errors or when you have one as an error, the model might, it might not help, right? It might not give out the correct number. So if it has no errors, right, 0, then you can't say that the accuracy is 0 or the whatever, right? You can't calculate it properly. And that's the reason why you use logarithm function to translate these numbers. So it's just a transformation so that you get some meaningful numbers out of it. That's it. Nothing major there again, right? So it's just terminology. Just remember that cost functions are nothing but the functions you use to evaluate the error your model has, right? Be it regression or classification, it's just the error that gets measured. And the function you use to measure that error or the metric, right? Metric is basically the final value you get, right? The formula itself is called the cost function. When you put values into the cost function, whatever number you get at the end is called the metric. Make sense, guys?
I think so, yeah.
Yeah, for example, let me give an example, right? MSE. The formula is sigma I is 0 to n, error 1 square by n, right? This is my formula, right? This is my cost function. Okay. Now let's say I have a data set for which I apply this formula and I end up getting MSC value. You remember in the code, right? Like you have MSC as a metric, mean squared error as a metric. So you can just call that metric from sklearn metrics library. You can just import it and then measure the mean squared error of a regression model, right? That's what you do with code. And let's say you end up with a number, so something like 12.134. Okay. This is metric. This value is metric. Okay. This value is what is referred to as a metric. This formula is what is referred to as a cost function. Make sense? Now, why this is called as function is this can be applied to a different data set or a different subset of the training set or an entirely different data set, and you'll get a different value. Each time you get a value, it's called a metric. But each time you can reuse the same formula, right? You apply the formula and that's how you calculate things. The formula itself is called cost function. The value you get by applying your cost function to the given training data set or whatever data set you have, the value itself is called as metric.
So the value is called a matrix.
Yep.
And the
Formula
is called
cost function.
cost.
Yep.
Okay. I mean, is there
Why-
a reason? Do we need
why-
to have this like memorized or?
It's because people ask you the questions on the interview and they try to,
Trick,
showcase
like a
that.
trick question.
Yeah. Well, trick question, you can say. Sometimes they just want to play around with you, right? They want to see if you know the terminology. It's just very stupid, I would say. But so why and where this actually comes up is when you're working with neural networks, right? In deep learning, you have everything comes up in terms of like functions. So this is how a network will be like connected, interconnected and stuff, right? So let's say this is a neural network, right? Everything here that happens in terms of functions, right? So there is an activation function for the neuron, right? Then there is a cost function associated with the predictions. So that is really where the terminology comes from. When you typically build a traditional model, right? Traditional ML model. With the traditional ML model basically means the models that you guys have studied so far, right? Linear regression, logistic regression. These type of models, you generally refer to them as metrics. But when someone from a neural network background is interviewing you, they tend to ask you what is cost function. It's just a way of calling it, right? Because for them, the formula is what matters, not the number, right? So it's just nomenclature. It's just a way of naming things. Don't be intimidated by it, because I was. That's the reason why I'm telling you guys. Because
I'm very intimidated.
Sorry.
I'm very intimidated by it. So Satwick, do you have like a and this is just out of nowhere with what we're learning, but mathematical background in all this? I mean, whenever they ask for somebody that has computer science skill and math and all that, or did you just start like one of us? Yes, stats and all that.
I wouldn't say it didn't have a background, but at the same time, I didn't have like a major focused background. It was one subject among my whole course. So my undergrad was in computer science. And when I was doing my computer science engineering, as part of engineering subjects, one of the subject was calculus, right? That's where they taught us a lot of stuff. They also had statistics, calculus. These were a couple of subjects that I had, but that was just in my first year. The last 3 years of my engineering was basically just computer science subjects like software, SQL, warehouse, neural networks, this kind of things. Then there was like my masters, two of my masters, like one master's was an MBA. Again, I did a refresher of statistics, but again, it was never focused. So it was again the same measures of central tendency, basic models and stuff. I never went into the depth of statistics. Same with my master's in MIS, Management Information Systems. It's the same there as well. Just one subject, statistics, that I elected. It was not part of our course. I took it out of my own interest. But again, not too deep, because when you go to when you go through these roles, right, some of them say that PhD in statistics or masters in statistics preferred. Those guys study statistics for 2 years, right? So they know a lot of various tests. They have a lot of knowledge. They understand all of these things. So typically in your interview, these are the type of people who will sit and ask you questions like, hey, what's a cost function, right?
Mhm.
And this is, I would say, a barrier in getting into a data science career. The glossary, the language, right? When they say metrics, or when they say optimization, when they say loss functions, cost functions, loss function and cost function is basically the same, right? But it's just it's like learning a new language, right? When you don't know what a loss function or a cost function is, you tend to get intimidated when they ask you this question in the interview, right? And then you might come out like, I had this conversation like a while ago when I was initially, looking out. So that person, and in fact, this is when I joined Colaberry initially. There were two interns who were working with me. This is a very personal account. So there were two interns who were working at Colaberry already, and I was just a new guy, just joined Colaberry. This was way back in 2017. So when I joined, those two guys were already someone from data science background. I didn't understand a single word they were speaking, because they were all like, cost function, loss function, that function, this function, that, this, RMSE, metric, evaluation, regression, classification, unsupervised, supervised. Just went above my mind. But later I understood that loss function is the same as cost function. Then why do you call it by two different names? It's because everyone, to each his own. It's just how the domain has evolved, right? It's also same as the metrics that you use to evaluate what is my error, right? That's it. Nothing, no rocket science here, right? It's just that people from different backgrounds, some of them are physicists, they come from, some of them are mathematicians. Physicists might say loss, mathematicians might say cost. It's just stupid of them to just, make up these words and just confuse someone who's trying to enter the field.
Think we can get a glossary of all this?
That is something that I've been thinking of building since a very long time. Let's see if
I
we can.
support you fully to build it.
Yeah. It would help, right? Like just getting
Yes.
to know the various words, and it will be helpful to just, refer to that glossary before you guys go to an interview. You can find all these terms and, exactly what they are asking for before you go to an interview. So yeah, that's something that I've been working for. Maybe it's time that I should put that to effect and actually, build something like that. But anyways, so far so good. You guys understand that the value itself is called the metric. The function or the formula that you use to calculate that particular value is called the cost function, okay, or the loss function. It's loss because it's failing to predict, right? This is all the error that it has, the error in its predictions. That's why it's called loss. Makes sense, no?
Yeah.
David, Susan, Liz, you, Eves, Jude.
Yeah.
So loss function, maybe would the term be used more with classification or not necessarily?
Not necessarily, because it could be regression as well, right? It's just that think of it as probably someone from a physics background will probably refer to it as a loss function. Probably someone from mathematics background might refer to it as a cost function. We just don't know. Like, it depends on how they studied or what they came across. They might just use these terms. Loss and cost are basically the same. So this, right, like now, what is gradient boosting? And the reason why I'm like taking this time to explain these to you guys is the XGBoost that we are going to discuss about is also based on this concept called gradient boosting, right? Now, what is, or gradient descent rather, not gradient boosting, but we'll talk about gradient descent as well. Has Pawan mentioned gradient boosting? I'm pretty sure he would have at least mentioned about it in DS2. Do you guys remember discussing about gradient boosting?
He referenced
Gradient
it.
descent.
He referenced it like when we're doing our project.
Mhm.
Because for my group, our project was classification, so he did mention it.
Okay, no problem. So what is the concept of gradient descent really? Right. So here we talked about a specific, MSC or a cost function, right? Now, I'll explain this with respect to linear regression. Okay. What happens in your linear regression? You remember you can fit various lines through the data set, but only one of them is the line of best fit. You guys remember that, right?
Sorry, can you say that one more time?
So you can fit hundreds of different straight lines through the data set.
Yes.
How do you decide which one is the best model? Right? The one with the lowest error. Remember?
Yeah.
The one which has the lowest error is the best model. So if you remember the ordinary least squares method, OLS method or whatever, right? The algorithm is trying to find the line of best fit. So it experiments with various lines and then it finds out that line. Now, how does it? So there are infinite different possibilities, right, of fitting lines. It doesn't experiment with infinite lines. So how does it actually reach the line of best fit in such a short span of time? Like when you train a linear regression model on a simple sample data set, how long would it take you guys? Right? It will probably take a couple of seconds and maybe maximum couple of minutes, right? It doesn't take longer than that for a simple data set, right? Now, for even such a simple data set, there can be infinite number of lines that can be fit through the data set. Now, how does it reach that particular, line of best fit? What happens here is it takes this particular cost function, or in my case, MSC, fits a specific line, calculates the MSC for it, right? Then fits another line, calculates the MSC for it, right? What it does is it starts analyzing these error rates. Let's say this is my MSC, this is my model or iterations. Let's say not model, iterations. Iteration basically means that in first iteration, I will draw a line like this. Second iteration, I'll draw a line like this. Third iteration, I'll draw. So fourth iteration, I might draw like this, right? So each iteration is a different line that can be fit to the data set. Okay. So the MSC might start off at a certain level, right? First line that I fit, let's say my MSC is 243, right? So it starts off at 243 here, right? The second line, right? Say it is again 243, 242, right? So it tries to bring the line, it will draw a line here, 243. It will try to bring the line closer to some of the points. It will try to bring the line closer. Then it will change the orientation. It will experiment in various ways like that and try to see how the error is improving, right? The idea is for this error to come down and as close as possible to, this is 0 level, right? This is my mean squared error. Okay. So I will optimize my model. I will move the line in such a way that this is so it's not random. If you guys understand what I'm trying to say here, right? There are infinite lines that I can draw here, but it is not interested in those infinite lines. What it does is it draws lines and then tries to measure the MSC and then tries to draw the next line in such a way that this MSC goes down, right? So again, it looks at the residuals, which means that it looks at the first derivative of the function and whatever, right? You guys don't have to bother about the math, but the concept here is it looks at the derivative. It looks at where what do I do in order to reduce my error? How do I move my line in order to reduce my error? That's where it learns that the closer it moves the line to the center of these points, the lower the error is going to be, right? That's how it plots these errors and that's how it learns. And this error keeps coming down with each new line or each new model it experiments with. And there will be a point where the error will become very minimal. Maybe it will be 12 or something. It will never go down to 0, because if it goes down to 0, you know there is something wrong with the model, right? So no model can be 100% accurate. If it is, there's an issue, or maybe that's a wrong case for ML, right? Well, so let's say it comes down all the way to 12 as a number, my MSE, and then it stays constant, right? This is called gradient descent, right? Descent, now you understand the idea of descent, right? The program is trying to minimize the error with each step, right? It's trying to minimize the error with each step. And this is what is called as gradient descent.
So what the gradient descent is doing is find the
No, gradient descent is not doing it.
Oh, it's not doing
It's
anything?
the model. It's the model. Gradient descent is a process of minimizing. Okay. Gradient descent is the process of minimizing the error. This phenomenon, right, that is happening is called gradient descent. So the model, the OLS model, the ordinary least squares model, right? This is the linear regression model or the linear regression technique, right? This is the technique which finds the line of best fit for a linear regression. This technique is what is doing the iterations. When it does the iterations, it plots the error. And this phenomenon of it reducing the errors to a bare minimum is called gradient descent.
Yeah, got it.
What do you call the OLS again? Ordinary what? Linear square?
Come again, Jude? I didn't hear you properly.
The OLS, what's it called again?
What is it calling?
Yeah, I mean, what is like the full
Well, it's
name of
asking what
OLS?
does it stand for? What does OLS stand for?
Yeah, ordinary least squares. OLS is basically ordinary least square, and least square is MSE, least MSE, right? Least squares. So the lowest number of error, right? That's basically the idea. So it's looking for the lowest number of errors. The way that it does is it measures the MSE at each point of time with each line that it experiments with. And then it tries to find the line of best fit. And it reaches the line of best fit when this curve flattens out, right? So this phenomenon of the error reducing is called gradient descent. And this is exactly the same phenomenon that is being employed by gradient boosted trees, XGBoost, right? So there are gradient boosted trees, then there is XGBoost as well. So gradient boosted trees is basically a tree which looks at the errors. And that's why I was saying, right, like the next tree always looks at the previous tree's errors and tries to reduce them, right? And that's exactly the concept of gradient descent, right? So the gradient, think of gradient as the error, the value of error, or the difference between the error of the previous model to the current model. That's the gradient, right? And it's trying to reduce with each model is trying to do better than the previous one, right? So that's the whole idea. So it looks at the errors of the first model, tries to improve upon those issues, those errors, works with those residuals, tries to minimize them. Whatever it generates, the next model works on that. So like that, there is incremental improvement in their predictions, right? And that's why XGBoost becomes, or gradient boosted trees become much better in terms of accuracy than a random forest. So always when you compare the accuracy, a boosted tree generally might give you better accuracy than a random forest, okay? Because it is improving continuously, whereas random forest is just training multiple trees parallelly, and it's trying to like average out all of their predictions.
Or you're saying that gradient boost is more accurate than random forest?
Yep, because it's learning from each other, right? These trees are communicating, these models are communicating with each other in the way that this supplies the next model with the residuals, with the mistakes or the misclassifications or the mispredictions, wrong predictions that it has done. It sends the residuals to the next model. So the next model looks at those residuals and sees, how can I improve on these errors? How can I not repeat the same mistakes? Yeah.
So why is random forest the go-to?
Yeah, that's what
Good question.
I
Good
was,
question. So do you
but-
see an issue with the way this is training right now? So both of them have, trade-offs, right? So this might not be as accurate as XGBoost, but there are some good things about random forest, right? Because it does bagging and it's averaging things out, right? It handles overfitting in a much better way, right? And you guys remember that it also reduces the feature set. It might not expose all the features in training a specific tree, so that way it works with different trees, and working with all these uncorrelated trees, it reduces the risk of overfitting. And at the same time, because these trees are trained individually and parallelly, it is faster, right? You have, let's say you have multiple cores in your processor, right? Each core can train one or two trees, and then you are parallelly training all these trees. Whereas with sequential learning, what happens? It trains the first tree and it has to complete training the first tree, complete building the first tree in order to go to the second model, right? Because it needs the residuals from the mistakes from the first tree, right? So think about it, that it is probably going to be slower than a random forest, and there is no parallel processing possible here, because each tree needs to communicate with the next one, right? I mean, needs to be fully trained, and then it says that, okay, these are my mistakes. These are the mistakes. These are the observations with which I made a mistake in prediction. So take these mistakes and then improve upon them. You won't know the mistakes until you train the first tree completely. And then you proceed to the second tree, right? And at the same time, because it's improving on accuracy, it also has a risk of overfitting, right? Because this might achieve a certain level of accuracy, and then the next tree works further on it, right? And then further, it might actually be looking at the noise in the training data set, right? In order to learn and improve and improve and improve, it might actually be trying to, it becomes complex over a point of time, and it looks at the training data set very sensitively, and it's more susceptible to outliers as well, right? Boosted trees are susceptible to outliers. You have one outlier, it tries to predict that particular outlier in order to do better. The outlier might not be predicted by the first model, but as you continue training it, right, it might try and predict that outlier, right, also in order to increase that accuracy. So you guys understand now that what the pros and cons are of both of them?
So is
XGBoost.
XGBoost. Doesn't it go like parallel?
It can't go
Like
parallel
boosted.
because no, it doesn't. So see the way it is training, right? Trains the first model completely, looks at the errors. It has to look at the errors of the first model. It can't look at the errors of the first model unless it trains it completely, right?
Okay.
Here, there is no communication, right? You don't have to wait to train the second tree. You don't have to wait to train the second tree, or wait for the first tree to finish training in order to train the second one. Or you don't have to wait to train the third one in order to let the second one finish. You can train them all in parallel. But here, this second tree is communicating with the first tree. It learns from the mistakes. Third tree learns from the mistakes of the second tree and the first tree, right? So there's incremental learning, right? So there is a dependency here in this case because of the sequential execution, and that dependency builds the delay in training.
Okay. So, but there's going to be like instances where random forest will be much better than XGBoost.
There could be, right? There could be. So let's say, for example, there is a data set where the random forest, has an accuracy of 96%. Boosted trees have an accuracy of 98%, right? For the 2% difference in accuracy, and let's assume that they are not overfitting for the sake of our case, okay? Let's assume they are not overfitting, they're good. 96%, 98%. For the sake of the 2% additional accuracy, are you willing to compromise on the speed of the prediction? right? Boosted tree might be slower in that case in order to come up with the 98% accurate prediction, right? So in that case, are you willing to like compromise on speed? You might go for a random forest, right? That 2% might not make much difference. So there are cases, and there might be some data sets themselves that, where boosted trees might be bad, random forest might be better, right? For example, maybe the data has some outliers, in which case boosted trees will try to predict the outlier as well, because they hate mistakes, right? Boosted trees hate mistakes. The whole concept of this sequential learning is to improve upon these mistakes and get the best accuracy possible, right? So they might learn and try and predict the outliers as well, in which case the random forest might be much more robust. Make sense? So there's a trade-off, right? Do you want higher accuracy, or do you want higher speed and much more robustness? Right?
Yeah, but the assignment that we're supposed to do, random forests at higher accuracy than the XGBoost.
Yeah, it is possible, because we don't know. It's hidden inside the answer is hidden inside the data, right? So you have to look at how each feature is distributed. What are some of the, what is the range of each of these features? You have to draw box plots. So there's a deep analysis that you need to conduct in order to finally understand, okay, this one feature probably has outliers. So this feature has a lot of variance. This feature is distributed in not so normal way. So these are some of the issues that might throw off an XGBoost predictor, right? So unless you look at the data and like really, visualize the data, and that's why you perform EDA, right? Exploratory data analysis. When you do that, when you look at each feature and then look at the combination and see how they are interacting within each other, that's when you can finally answer the question of, okay, this is the reason why XGBoost is probably, doing well, or random forest is doing better than XGBoost or something like that. Make sense, Jude? Yep. And that's why you guys have to perform EDA. Although, see, it's not so easy to finally say that, the moment you do EDA, you cannot say at this point that, hey, XGBoost is going to be better than random forest, right? It might come with a lot of practice and a lot of experience that, when you do EDA finally, you might probably end up saying that, okay, these are how my features are looking like. Maybe in this case, it's going to be better for me to do. Instead, for us, the better thing to do is, instead of, because you can do a lot of EDA, you can visualize every feature, you can build so many different plots to give you so much different information about every feature in your data set. But when you have 100, 200 features, you can't, bother yourself with that. Rather, the easier thing is just apply the model, throw the model and see what numbers you get, and then pick the better one. Make sense?
Yeah.
That's why people typically don't tend to, spend so much time with EDA. Although it's a good practice to do that and understand, you don't spend so much time. You might build a couple of plots just to see do some basic checks, but you won't dig deep into the data to understand it from such a level that you are able to say, hey, this is better than that or so. Okay. All right. So again, there's one small difference I want to talk about, right? So the gradient boosted trees that I talked about and XGBoost, the only difference between gradient boosted trees and XGBoost is a gradient boosted tree. It's just a different implementation of gradient boosted tree. This is where, again, you might think about it, right? I just told you guys that gradient boosted trees are slow, they don't work well, and that's the reason why you might go for random forest and all of that. So there was a scientist called Tianqi Chen. Okay, he was basically from a very good programming background. So he worked on implementing these XGBoost in such a way that they are very fast, and that is why XGBoost. That's why it's called XGBoost. So they wanted like what do you call? multiple times, right? X basically means that X number of times it is improved, right? It improves by X number of times, or it is faster by X number of times. That's basically what it is. So I don't know how it is implemented on the back end to make it so fast, but it's a much faster version of gradient boosted trees. So it's almost close to a random forest, let's say, right? Now, which one would you use is the question. Again, just experiment with both of them, see what accuracies you are getting. If you do get better accuracy and you feel like it's not overfitting, go for the XGBoost. If you feel like, no, I'd probably compromise, it's just 1% or 2% accuracy, but I'm reasonably sure that random forest is much more robust for outliers or any, what do you call overfitting. It doesn't overfit. When you know that this is a better case, then you can go for random forest. It's a completely subjective call about which one you pick, right? But basically that's what XGBoost is. It's a much faster implementation of a gradient boosted tree. The same concept that we just discussed, right? The gradient descent phenomenon, using which they reduce the error by each successive model, right? Each successive model in training tries to reduce the errors of the previous one, right? And it goes to a certain level where the errors flatten out, and that's where the training can be stopped, right? That's where you can say that, okay, there is no more improvement that can be achieved, and this is it. Make sense, guys?
Yeah. So in general machine learning stuff, which of the models is being used more often?
Right, that's a good question. So XGBoost is something that is, you can see in a lot of places, a lot of people use XGBoost. At the same time, random forest is also equally competitive, right? But beyond these two models, XGBoost and random forest, you rarely see, like, there is actually a survey. I can look it up. I don't know if I still have it, but there was actually a survey that was done among a lot of about 100 or 200 data scientists, and there were questions saying that, what are the models you guys use more frequently? So if you think about those surveys, a lot of those surveys will basically have random forest, XGBoost as some of the top models. Very few cases you will probably see logistic regression, SVM, or linear regression or something like that. Very rarely you will see them, because oftentimes what happens is they might experiment with that model, but what happens is random forest or XGBoost usually tend to give much better performance. They are faster than a SVM. So, people end up picking a random forest or an XGBoost. If it's much simpler, then they might go for logistic regression or linear regression even, right? So let me look at that survey. If I have that, I'll share. It's interesting for you guys to also know what kind of models typically people would use.